Hey everybody, and welcome to our presentation on measuring the Earth, Moon, and Sun. We're going to talk about some stuff today that's really old science and really old math, which I think will be really kind of interesting for us. It's a way to measure some of these really important numbers in astronomy. When we look up in the sky at night, it's not intuitive that the sun is really far away and big and the moon is relatively close and small, or that the stars are made of the same stuff and look very similar to the sun, but they're just much larger. These things aren't clear when we look in the sky. But astronomers for centuries have known these things, for millennia really. And so it's because of some really cool science and some really cool mathematics done by people nearly 2,500 years ago. So how did we figure this stuff out? How did we initially determine how far away these objects were? Well, really, it was with geometry. Was using geometry. And this geometry, like I said, is centuries old. Some of the stuff that Greek astronomers / mathematicians came up with really defined the field of geometry and answered some of these fundamental questions in astronomy. Their ideas, which are over 2,000 years old, their methods are still right. What was different and what's changed is our ability to measure these things. There was nothing wrong with their methods, just their technology to measure things effectively. But these principles of geometry have lasted for centuries, and the rules that they figured out still work now. So we're going to talk in those terms, talk about some main principles of geometry. So geometry is really simple, right? It's a discussion of the relationship between lines and angles. It's sort of, if you know a line, and you know the value for that line, and you know an angle, you know the value for the angle, then maybe you can figure out another line or another angle. And it just keeps working with this process. If you understand a few rules, you can apply those rules and learn more values. And so if you apply the rules to the current situation, you can figure out more lines and keep going. For example, and I apologize for what's going to clearly be bad lines here, but if you have these two parallel lines and this line coming through it, and you know this angle, well, you also know this angle. And you also know these angles because the first two were parallel. And then you also know these because you know lines add to 180. And you can figure out all of this stuff. If you know one angle, you can figure out all of these values. And this kind of stuff happens over and over in geometry, where we use one little set of information to inform other sets. A lot of what we're going to talk about today is going to follow exactly this format, where if you know this thing and this thing, you can figure out this thing. And once you know that, you can use that third thing to figure out other stuff. And we're going to build on our discoveries to build a really strong understanding of some astronomy and some distances. Throughout this PowerPoint, you're probably going to pause your work every once in a while to actually calculate the values on your own. On your worksheet, you're expected to show some work. I generally give the answers, but you're going to have to work through and get some stuff on your own. Another thing that's worth pointing out is that it's not important that these answers are exactly right. It's important that they're close. When we're talking about how far away the sun is, if you're off by a few hundred miles, really it's not a big deal. It's that it's way farther away than the moon. Those are the kinds of level of information that we want to know. Okay, so to do this, we need to start by talking about circles. So just a quick review of how circles work and sort of the math of circles. This is how we figured out the distance to the moon, and it's part of how we got stuff to the sun and planets. But when you think about circles, there are, of course, three lines that are relevant. There's the diameter, the radius, and the circumference. And hopefully you remember these from geometry or basic math classes. The radius goes from the center to the edge, the diameter all the way across through the center, and the circumference is the edge. It's the circle that goes around the outside. So the easy relationship, of course, is the diameter to the radius. The radius is, of course, 1/2 of the diameter, where the diameter is 2 times the radius. And so understanding this information was pretty basic to even ancient astronomers and mathematicians. The big thing they tried to figure out was the relationship between the diameter and the circumference. And this is where our really cool number comes up that you guys all know now, which is pi. If you take that diameter and multiply it times the number pi, you get the circumference. Now, they didn't have a good value for pi. This is one of the things that we had to measure later on. They used 22/7 for the most part. But it still is a pretty good way of expressing this, and they understood the concept. Of course, we can do some substitution here too. If we want to talk about the circumference in terms of the radius, we can put that value in there too. And of course, since the radius is half the diameter, 2 times the radius gives us the diameter. So circumference is also equal to 2 pi r. So if you don't have these written down already, you should. If they're not in your head already, these are some valuable things for what we're going to talk about. Because, again, the idea is simple. If you understand the relationship between these lines, all you need is one value, and you can figure out the other two. If you know the radius, you double it to get the diameter, and you multiply that times pi to get the circumference. So you can figure out all of these if you know any of them. So we're going to work on this table on your worksheet throughout the entirety of this lab. You're going to go back and forth between figuring out different things and filling in this worksheet. Really, there's some numbers on here that we really want to know. The big ones are the sizes of these objects and the distances between them. The size of the Earth, we can talk about size in a bunch of different ways, but we'll generally talk about size in terms of diameter. So knowing the diameter of the Earth, the diameter of the Moon, and the diameter of the Sun give us relative sizes to talk about with regards to these 3 really important objects. We also care about the distance between these objects. And in the case of the Moon, the distance from the Earth to the Moon is the radius of the Moon's orbit. And so that's something we're also going to try and figure out. And probably the most important number in all of astronomy is this number here, the radius of the Earth's orbit, or the distance from the Earth to the Sun. And we're going to talk about why that's so important at the very end of what we do. So we're going to figure out these other values, in part because they help us figure these ones out. But these are the big ones we care about. Now, as far as this right-hand table, any good astronomer would have known this stuff. Would have known that it takes the Earth 24 hours to spin, it takes the Moon 27 days to go around once, and it takes the Moon the same time to turn once, and of course it takes the Earth 365-ish days to go around the Sun. So we know that information, and that can be helpful to figuring out some of this other stuff in somewhat surprising ways. So how can we start filling out the rest of the table? Well, if you recall, months and months ago, we talked about the value of Eratosthenes and his famous experiments in Syene and Alexandria in ancient Egypt. What he did is he figured out that if you go to these 2 different cities on the same day, on the summer solstice, there is a shadow cast in Alexandria to the north, and there's no shadow cast in the city of Syene to the south. And this is, of course, we know now because the sun sits above the Tropic of Cancer there during the summer solstice. And so it sits right above Syene, which is why we have no shadow there. And but it doesn't sit right above something farther north. But he used this discovery to explain that the Earth is curved. But not only that, he used it to figure out exactly how much the Earth is curved, or in other words, the entire circumference of the Earth. So how did he do it? Well, just reviewing, remember he had these 2 sticks in 2 different locations on the surface of the Earth. He paid a guy, supposedly, to walk the distance between them, so he knew the distance between them was 800 kilometers. He knew that the sun, well, he assumed the sun was really far away, and therefore you have these very, very distant lines, or rays from the sun, coming in parallel. In the city of Syene, that ray comes in straight down the stick, so you get no shadow. But in the city of Alexandria, it comes in a little bit of an angle, and you actually end up seeing a triangle between the tip of the shadow, the tip of the obelisk, or the tip of the stick, and the ray that's made by the sun, the invisible ray. And so we can measure that angle that's created by that triangle. And that angle turned out to be 7 degrees. So he figured out this angle was 7 degrees, and then with a little geometry, he used that little bit of information. He knew that this was 800 kilometers between them, and the angle was 7 degrees. He used those 2 things to figure out the circumference of the Earth with surprising accuracy. How did he do it? Well, you extend these 2 points right into the center of the Earth, and you get a slice of the pie that is the Earth. We know that 800 kilometers is the distance between those 2 points, and that's represented by this little slice of the pie. Well, if you extend these rays out, you have 2 parallel lines, these 2 parallel rays. And we know if this angle is 7 degrees, understanding interior angles, that this angle here must also be 7 degrees. So 7 degrees represents an 800 kilometer slice of the pie. So all we have to do is put together a ratio here, and we can talk about the entire size of the circumference. So 7 degrees is to 360, as 800 is to the entire circumference of the Earth. And we go through the math, a little cross multiplying and whatnot, and we get a value of around 41,000 kilometers for the circumference of the Earth. Now it turns out Eratosthenes was wrong. This isn't the right number. But he wasn't wrong by a lot. He was wrong by about 3%, which is pretty impressive given the tools he was working with. But this is the actual circumference of the Earth, around 40,075 kilometers. So we can put that into our table now that we know the circumference of the Earth. And if we know the circumference of the Earth, we can use that value to figure out the diameter and radius. To get from the circumference to diameter, we take that number and divide it by pi. And to get from diameter to radius, we take that answer and divide it by 2. And so if you work through that math on your own, I'll give you a chance to pause here. If you work through that math on your own, you should get values that look like this, where the diameter is about 12 to 13,000 and the radius just over 6 kilometers in diameter and radius. So we knew all of this stuff with regards to the Earth. And once we knew these values with the Earth, we could start talking about the moon and then eventually the sun. So how did we use this information to get to the next level? Well, in order to do this, we need to talk a little bit about a concept called angular size. When determining the distance to and size of an object, there are 3 values that we care about. We care about how big the object is in actuality, and like we said, we're going to use diameter to talk about that. You care about how far away the object is, and we'll use kilometers to measure that. And then finally, the last thing you can talk about is how big the object appears. This one we don't care about as much, but it turns out it gives us a relationship between the other two that's really important. So let me explain angular size a bit. So angular size is how much of the sphere of what you can see an object takes up. So if you have this little moon thing here, and you're looking out at it, it would take up about 13 degrees of your field of view at this distance. If it was farther away, it would have a smaller angular size, even though it didn't change in size at all. If you move it up closer, it has a greater angular size, all because of a change in how far away it is from you. So there has to be a relationship between its angular size, its distance, and its actual size. And it turns out there is. So again, there are these 3 numbers we care about, and we're going to represent them this way. Alpha is the angle between the edges of that object, so the angular size the object represents. So angular size is how big it appears to us. We can also talk about the actual size of the object, or its diameter, d. So that's there's a clear relationship between angular size and the diameter, and so we'll use that. And then finally, the distance to the object. And we'll think of the distance to the object as a radius of a great big circle. It'll be really relevant to us in our discussion. So we'll use r to talk about the distance to the object. It helps us distinguish it from d too. So is there a relationship between these 3? It turns out there very clearly is. 360 degrees is related to the circumference of your circle. So there's a very clear relationship between 360 and whatever value you have for the circumference. Well, similarly, whatever slice of the pie you're talking about has a relationship to that bit of the circle. So alpha has a relationship to d, or that section of the circle. So we can talk about the two together in these very simple ratio, where 360 is to the circumference as alpha is to the letter d. So as alpha is to d. So we have this really clear relationship here. Now, if you're being nitpicky, you understand that this d isn't a straight line that's going to be exactly like your angular size. But for small angles, the d that's the arc of this circle and the d that's the diameter of your object are really going to be close. So if we move on a little bit, we can remember that not only is this a relationship between the diameter and circumference, but we can put in the radius too. And that radius is what we really care about because it's a distance to objects. So we can put a little conversion in here where we replace diameter with the radius, and now we have a really useful equation. So if we know any two of these objects, the diameter of the object itself, the distance to the object, or the angle, we can calculate the other two. We need 2, and if we have 2, we can figure out the third. So for example, let's say you knew the alpha was 13 degrees for an object that was 10 meters away. In other words, an object that's 10 meters away looks about the size of your fist with a finger next to it. So a little bit bigger than your fist. So your question might be, how big is that object in actuality? And so all you have to do is plug those values in, and you can figure it out. So if you know 10 meters is the radius, and you know it's a 13-degree arc, you can plug those into this equation, and you should get a good value. I'll give you a second to do that if you want to try it. So again, plugging in 10 for r and 13 for alpha, doing some cross multiplying, dividing, and whatnot, you should get a d of about 2.27. And we can do this with real objects too. We just need to know either the r or the d. And if we know one of those values, we can calculate all the other stuff. This method, of course, also works if you know d, but not r. So you just need one of those two, and we can get the rest of the information. So what did the Greeks actually know? How could they get us anywhere? Well, like we mentioned before, they knew, thanks to Eratosthenes, the circumference and diameter and radius of the Earth. They also knew the angular size of the moon and sun. It's not hard to figure those out. You just need to look at them and see how much space they take up in your sky. And with a little bit of measurement, you can figure them out. Now, we have a total coincidence on our planet that these two things have the actual same angular size. And you can approximate it by holding your finger up at arm's length. Your finger represents about 2 degrees of arc distance, and the moon can easily be covered with your finger. Same thing with the sun. And that's because the moon and sun have an angular size of about half a degree. So it's a pretty small amount of the sky that they take up, which is amazing given how bright they appear in our sky. But we know that alpha. We know that the alpha is 0.5 degrees. So can we figure anything else out with this information? Well, again, here's the list of things that we know. We know the circumference of the Earth, the diameter, and the angular size of these two objects. So enter our hero, Aristarchus of Samos. So this guy made a couple of observations and knew a few rules of geometry and came up with some really good stuff here. To begin with, he knew that a lunar eclipse takes about 3 hours to happen. He also had an understanding of why lunar eclipses happen. It's because the moon, orbiting the Earth, passes into and out of the Earth's shadow during its orbit. He also knew that it took 27 days for the moon to go all the way around, one complete time. But believe it or not, with those bits of information, you can actually figure out how fast the moon is moving and therefore how big the circumference of its orbit is. So how do we do it? Well, to begin with, when we think about the moon, of course, it has this giant orbit around the sun. And like we mentioned, lunar eclipses happen because the moon passes through this shadow that's cast behind the Earth. Well, we know that the diameter of the Earth is about 12,700 kilometers. Aristarchus assumed, and he was pretty close, that the diameter of the Earth's shadow would also be the same 12,757 kilometers. So if the shadow is the same, we know that the moon is passing through this distance during a lunar eclipse. And that it took 3 hours to do that. So this isn't complicated. If we know it goes all the way around in 27 days, and we know it goes through a lunar eclipse in 3 hours, the math is really pretty easy. If it takes 3 hours to go 12,757 kilometers, how far are you going to go in 27 days? Well, the math here just requires that you replace 27 days with hours by multiplying 27 times 24. Now, you're asking, if it takes 3 hours to go 12,000 kilometers, how long would it take, how far would you go in 648 hours? Do a little dividing. You figure out the moon's moving just over 4,000 kilometers per hour by dividing 12,757 by 3, and then multiply that times 648, and you get your value for the circumference of the moon's orbit. So do the math, and you get something that looks like this. Now, this number is not exactly right, and the reason it's not exactly right is because we're making a lot of estimates here, and also one of Aristarchus' assumptions was a little off. The shadow of the Earth isn't exactly the same as the size of the Earth. It's a little bit less, And it's a little bit less because the sun isn't just a point of light, it's a big disk. And so some of the rays of the sun are getting in around the Earth, resulting in that passage of time being about 75% of the Earth's diameter, not the entirety of it. So with this correction, we get an actual circumference of the moon's orbit of about 2.16 times 10 to the 6 kilometers, or just over 2 million kilometers. And we can again plug that value in for the circumference of the moon's orbit. Once we know the circumference of the moon's orbit, diameter and radius are easy. I'll give you a second to figure that out. And hopefully you had a chance to pause and do it. Circumference, we divide by pi to get diameter, divide that by 2 to get radius, and these are our approximate values there. So now we know how far away the moon is. The circumference was cute, but now we know the radius of the moon's orbit. And again, the radius of the moon's orbit is how far away it is. That's one of the big numbers we wanted. Now, if we know how far away the moon is, we can start working with its angular size to talk about how big it is. So again, these are known values to me. I know the distance to the moon. I know the angular size of the moon. And all I have to do is plug through this equation and I can calculate the diameter of the moon. So I put in 0.5 for alpha and I put in 384,400 for r, run through the math, and I get something like this. Where if I plug it all in, I get a value very, very close to the actual value. Depends a little bit on what you use for pi, but we can use a value of the correct value, even though this one was a little off. Again, it's a pretty good estimate. Our correct value of about 3,474 kilometers for the diameter of the Earth, for the diameter of the moon. Again, once you have diameter, circumference and radius are easy. We divide that by 2 for radius, multiply it times pi for circumference, and we can calculate those values. So once again, I will pause so you can do that on your own. Hopefully you did it. Here, of course, are the values, just a little bit more and just a little bit less. Okay, so now we have all this information for the moon. Can we do the same thing for the sun? Well, it turns out we can, with a little bit of a different bit of math. So how do we figure out how big the sun is? Well, we know the angular size of the sun, so we have its alpha. We need either the distance to or size of the sun for the rest of our data. And the way we can do this, even though the Greeks who first did this didn't use trig, the best way to do this is to use triangles and trigonometry. And so we'll go over some basics of those before we get started. So this guy, of course, is Pythagoras, and he's sort of the king o' triangles. And Pythagoras, of course, came up with a relationship between the sides of a triangle. He figured that in a right triangle, the hypotenuse C is equal to the two other sides squared if you took the square root of that. So in other words, a squared plus b squared equals c squared. So with the Pythagorean theorem, if you had any two sides of a triangle, you could figure out the third. And this is valuable information, but in terms of figuring some stuff out in astronomy, we really need a little help here. We can calculate one of those lines, an r if you will, or a d, but we really need an angle here. So in trigonometry, all we need is a side and an angle, and we can figure everything else out. So if I knew the length of b and the angle it makes with c, I could actually figure everything else out using the relationships between sine, cosine, and tangent. So we'll go over this really quick. It's beyond the scope of the class to know trig, but it's good stuff to know because this is really part of why they invented trigonometry, is to answer these kind of questions. So really briefly, trig again is a discussion of the relationships between angles and sides in a right triangle. So if my triangle has an angle that's 90 degrees here, we can talk about the parts of it, or the anatomy of the triangle. The side that's far away from it is the hypotenuse. If we put another angle in here, so our angle alpha, we can talk about the side of the triangle near our angle as the adjacent, or next to, and the one on the far other side as the opposite. They're just in relationship to that angle alpha. It's not their size, it's whether they're close to or far from alpha. So when using trig, we use this acronym SOHCAHTOA to figure out what's going on. The first letters here, the letters S, C, and T, tell you which function you're using. So either you're using the sine, cosine, or tangent function. The OH, AH, and OA are these letters here. H for hypotenuse, A for adjacent, and O for opposite. So they're telling you which sides you're using. So for example, if we want to try to find out the length of the hypotenuse, given this angle here of alpha and the adjacent value of 12, how would we go about it? Well, the first part is figuring out which two things we have. We have the value for the adjacent. We, of course, have the angle value alpha. And in this case, we also have the hypotenuse h. So we want the function that uses the two things we have or are trying to find, h and a, and then alpha. So if you look up here, the cosine function is the function that has h and a in it. So that's the one that we're going to use. And the way this acronym works is it says that's this function and then something over something. So this is the cosine of the adjacent over the hypotenuse. So it's the cosine of alpha is equal to the adjacent over the hypotenuse. So all we have to do is plug in our values, again using this CAH. So our cosine of alpha is the cosine of 28 is equal to 12 over h. So all you have to do is turn your calculator sideways if you're using your phone, type in cosine 28, that'll give you a small value, and then take that value and take 12 and flipping it around, divide by it. And you'll get a number for the hypotenuse of around 13.6. Again, just putting in the cosine function and that value 12. You can do the same thing with like finding the opposite, but if you're trying to find the opposite, we have an opposite and a known value for adjacent. We're going to use the tangent function in this case. So we use the tangent function. Again, it's going to be opposite over adjacent. So in our case, it's opposite over 12. We plug through this, and this time we end up multiplying, and we get an opposite of about 6.4 meters. So again, this is just basic trig, but it's the stuff that we're going to use to figure out how far away the sun is. So how we do it? Well, again, we're trying to figure out these last little bits of information, which are hugely important. So to begin with, what Aristarchus used to figure this out was a quarter moon. And a quarter moon, if you do a little bit of thinking and moving balls around in the sand, you can figure out that a quarter moon, we see a quarter moon when the lineup between the Earth, Moon, and Sun forms a right angle between the Sun, Moon, and Earth. This is when the half of the moon that's lit up shares half of that with the half that we see. And that's why we see that half moon or that quartered moon. So if we have a 90-degree angle, we have a right triangle. We just have a right triangle with a really long and really important hypotenuse, which is the distance from the Earth to the Sun. Now, if only we knew this stupid angle here and one of those two yellow lines, we could figure out the hypotenuse. Well, it turns out we do know one of those yellow lines. We know from our last stuff the distance from the Earth to the moon, right? We know that value, and that, of course, is the adjacent. It's the value right next to our angle in this great big hypotenuse. So this distance, again, is the radius of the moon's orbit. So if we look at it, that's that value, 344,520. That's the value for A, or our adjacent. So now if we know that angle alpha, we can figure out the distance to the sun, which would be so amazing. So we can figure it out, and the way we figure it out in principle is really easy, in practice is a good bit harder. But here's how it works. When we're hanging out here on Earth, you can look up in the sky in the daytime when the moon is quartered, and you can see both the sun and the quarter moon at the same time. Well, your angle alpha is the angle between these two guys. So all you have to do is literally go outside and point a stick at the sun and point a stick at the moon and measure the angle between them. And if you measure that angle between them, you'll get your value for alpha. So in our case, when Aristarchus measured this, he got an angle of around 87 degrees. Now, 87 degrees is a really close to 90-degree value, And so he ended up with a sun that was good and far, about 20 times farther away than the moon is. Now he was wrong by a lot. Turns out it's more like 400 times. But his principle was right. It's just his angle was wrong. It's really hard to figure out when the moon is exactly quartered because it looks close to it for such a long time. When the moon is quartered, we actually get an angle very, very close to 90, 89.87. You can take this number, plug it in for your alpha, and then do a cosine function to retrieve that length of that hypotenuse. So you plug in that alpha value, and you plug in that adjacent value, plug through, do the math, and I'll give you a second to do it if you want. And when you do it, you get an h value of about 1.48 times 10 to the 8 kilometers, or 148 million kilometers. And again, this is one of the most important numbers in all of astronomy. It's the average distance from the Earth to the Sun. Well, remember, this super, super important number is a radius of a giant circle that is the Earth's orbit. So if we know this radius, which was the hypotenuse of a triangle a minute ago, we can figure out the rest of those values. You take the radius, multiply it times 2 to get the diameter, and then that times pi to get the circumference. So I'll give you a second to do that if you like. And here are those values, 9.3 times 10 to the 8th kilometers for the circumference, and a diameter of twice the radius. Okay, now we're on to our last little bits of information. How big is the sun? Well, if the sun's really far away and it appears the same size as the moon, it's got to be really big. And again, all we have to do is use this same equation. But in this case, we're putting in values for the sun instead of the moon. And I'll let you do this on your own if you want. Remember, our alpha value is half a degree, and our R value is the radius, is that hypotenuse we just figured out, or the radius of the Earth's orbit. Plug those in, you should get a number that looks something like this. The diameter of the sun being right around 1 million kilometers, 1.4-ish million kilometers. No struggle. So if you plug them all in, you get a value for the radius of the sun. So if you plug them all in, you get a value for the diameter of the sun right around 1.4 million kilometers, or 1.39 times 10 to the 6 kilometers. Once we know the diameter, again, radius and circumference are easy. We divide by 2 and multiply times pi, and we get values that look like these. So there we go. We got our entire table figured out with really just 2 factoids about astronomy. Well, 3 if you count Eratosthenes. We know that we have shadows in one spot. We know about lunar eclipses and how long it takes the moon to go through them. And then we know the relationship between Earth, Sun, and Moon during a quartered moon. And these give us these very, very important values. And we can reconfirm them through other methods, but this is a good place to start. Now, I mentioned before, all these values are important, but the radius of the Earth's orbit is the number in astronomy. Why? Because it's the distance from the Earth to the Sun. And we actually don't call it anything other than the astronomical unit. It is the number in astronomy. So the astronomical unit, or an AU, is the average distance from the Earth to the Sun. And it's 93 million miles, or 143 million kilometers. But this is an incredibly important number. So important that we don't call it an or one astronomical unit. We call it the astronomical unit. So the astronomical unit is the average distance from the Earth to the Sun. And I don't know about you guys, but for me, these numbers are so big all the time that I find it helpful to talk in numbers that are smaller. You tell me like, oh, the Jupiter is 80 million bazillion miles away. Like, man, that just sounds like a big number. I don't know what that means. But if we talk about our solar system in astronomical units, it actually makes a little bit more sense. Now, you don't have to replace these on your worksheet, but realize that we can talk about the radius of the Earth's orbit as 1 AU. So that makes the diameter 2 AU and the circumference 6.28-ish AU. Now we're saying, okay, the Earth's, moving 6.8 times around for what its radius is. And if we talk about other objects in the solar system in astronomical units, we really have values that make some sense. Say, how far away is Mars from the Sun? Well, it's about 1.5 AU, or 1.5 times farther away than the Earth is. That makes sense. Or Saturn is almost 10 times farther away from the sun than the Earth is, at 9.54 AU. So this makes for much better discussion and doesn't bog our heads down in really big numbers. And it turns out that knowing this astronomical unit, knowing its value, helped us launch out to talk about all these other values in the solar system and beyond. We could talk about values for planets and how far away they are, and then the stars themselves. And so we will talk about those things in our next lesson. Thanks so much. Hope you enjoyed, and good luck.